I'm here with Jessica Olark and Richard Guerrero, right? This is another great video. We're going to talk about circular motion, right? And we're going to talk about this idea of centripetal force. Now, we learned in the past that in order to have an acceleration, the velocity has to change, which means that either the direction, okay, or the magnitude of the speed of the velocity have to change, or both, right? So in this case here, we're going to do uniform circular motion, meaning like the speed stays constant, but the direction changes. We're not going to complicate it where it's like the speed changing as it's turning. So a simple example is like if you take a tennis ball and attach it to a string and you just whirl it over your head, okay? And if you can maintain a constant speed, that's a circular motion, right? Now, what's forcing this ball to kind of like stay in a circle? It's basically the string, right? If it wasn't for the string, if I do this, if I let the ball go right here where my left hand is, it will just go flying towards that wall. There's a wall over there. Okay. So now there are some formulas that we're going to deal with. Maybe I'll show you the proof in another video, maybe not, because I'm more interested in like doing the math and understanding this conceptually than proving a formula. Now this is the definition of revolution and rotation. Revolution is when you turn it around something outside of you, meaning like the earth revolves around the sun. Rotation is when you're spinning around the internal axis. And we'll do that when we talk about rotation. It's a whole unit on this. And rotation is like the earth spinning on itself or rotating on itself. The velocity vector is always tangent to the path. We've learned that in the past. At all times, the velocity is always tangent to the path. So if you fire a projectile and it does something like this, at this moment here, you're going tangent to this path here. At this moment here, you're going tangent to that path. So you're constantly changing direction. In here, you're changing direction and magnitude. The net centripetal force is the vector. Okay, there is no such a thing as a centripetal force. A centripetal force is basically the combination, right? The net of all the forces pointing towards the center and away from the center. So we're going to choose towards the center as positive, so it's going to be anything that's directed towards the center minus anything that's directed away from the center. This will make more sense once we start doing the math. We'll look at different examples. All right, so here are the formulas, and I'm going to try to just explain the formulas, do a few examples, and that's it. Okay. AC, that's the centripetal acceleration, equals v squared over r. There is a proof to that. Maybe we'll do it, maybe not. Now, why do we have this centripetal acceleration? Because our velocity is changing direction. Okay. Now, let's say if this actually makes sense. If you go fast, right, there is a greater change in direction because you're moving fast. So your direction is changing quickly. So your acceleration is higher. So we understand the direct relationship between the acceleration and the speed because you're changing that direction pretty quickly. Now what happens if you make r large? Just imagine, if you make r large, the change happens slowly. Change in direction, that is. So there is that inverse relationship. Okay. Now, where does this F net C comes from? Well, this is Newton's second law. F net equals ma. Okay. Now, if you put these two together, you end up with this equation. Now, this is just speed equals distance over time. So if I take this tennis ball and I go around like this, and if I know the radius of this string, or based from the center of the ball to where my right hand is, the speed is the circumference divided by the time it takes to do one turn, one revolution. All right. Okay, let's look at some applications of this. So the F net centripetal is mv squared over r. Now this is going to change. There is no such a thing as a centripetal force. So in the case of the tennis ball, the centripetal force is pretty much the tension in the string. Now if I take this tennis ball and I go with a vertical circle, right? Now, the centripetal acceleration is different. So when the ball is up here, you have the weight pulling down, right? And the tension going up. Okay, I'm sorry, they're both pulling down. The weight, the mg is pulling down, and the tension is also down. So your centripetal force is the sum of those two. When you are down here, you have the tension going up towards the center, okay, minus the mg. That's the centripetal force. Now, if you